Greetings, everyone. Welcome to the ION webinar featuring the paper Residual-Based Multi-Filter Methodology for All Source Fault Detection, Exclusion, and Performance Monitoring, published in the Fall 2020 issue of Navigation. Today's webinar will be presented by one of the paper's authors, Dr. Juan Jurado. Please note, this paper is available to download from our website. Lieutenant Colonel Juan Jurado is the Director of Education at the U.S. Air Force Test Pilot School. He holds a BSEE from Texas A&M University, an MSFTE from the Air Force Test Pilot School, and an MSEE and PhD from the Air Force Institute of Technology. Previously, he served as Director of Engineering for the 413th Flight Test Squadron and oversaw various C-130, B-22, and H-1 flight test programs. His research interests include aircraft performance modeling, online sensor calibration, image processing, visual inertial navigation, and statistical sensor management for multi-sensor navigation problems. We greatly appreciate the time and work that Dr. Jurado has put into this. Following the presentation, Dr. Jurado will take some questions. To ask a question, please click on the Q&A box on the lower horizontal navigation bar. So thank you for being here, and now I will turn it over to Dr. Jurado.
Thank you very much, appreciate it. Can you hear me okay? Perfect, thank you so much. So good morning for those of you on the West Coast, good afternoon for everybody in the East Coast. My name is Juan Jurado. I am a officer here in the Air Force Test Pilot School, an instructor and a staff member. And I'm a recent graduate of the Air Force Institute of Technology, where I worked on this specific research with Dr. John Roquette, which a lot of you know from ION. This paper, as recently published, as mentioned in the introduction, is it's called Residual-Based Multi-Filter Methodology for All Source Fault Detection, Exclusion, and Performance Monitoring. And what we're going to focus on really is this idea of all source. We've seen a lot of fault detection FDE algorithms in literature for a lot of different applications. What John Roquette and I wanted to do, along with our other authors, is to come up with an algorithm that is capable of performing some of the techniques that we know and love for FDE and integrity guarantees, but in a system that is informed by not just satellites, but sensors of all types, which is something we've been working on for a couple decades now, this idea of all source or alternative navigation. So this is what this paper is about. It's a simple, straightforward algorithm that we're proposing here that includes fault detection using residual test statistics across a variety of sensors. And then also a new proposed sort of measure of integrity that is a little different than what we've seen before, also in a fault agnostic or sensor agnostic manner. So we'll get started in just a second here. All right, so the research motivation, which I just alluded to, is really to design an all source FDE algorithm. And what we mean by that is something that is capable of detecting and excluding faults in a way that is sensor and fault agnostic. And we'll get to what that means in a couple of slides later. But really in a way that does not make any assumptions about the type of sensor that you have on the system or sensors, or the type of fault that you're looking for. And so that was a particular challenge for us when we looked at existing methods. The other thing that we wanted to make sure we could do is interface or have an algorithm that doesn't really constrain the type of the synchronicity of the sensors. So the idea that our sensors, for example, if you're thinking in an all source system, you have a visual aided navigation system, you have a magnetic aided navigation system, you have your satellites that you're working with. They're coming in at different update rates at different times. And the idea of having synchronous redundancy, or the idea that I have overlap and redundancy at every single sample, is not necessarily guaranteed. And so we wanted an algorithm that could also handle that kind of situation, which is heterogeneous, meaning sensors that have different measurement models with different dimensionality of the Z vector, which is the measurement vector, and different sensor types. And they're asynchronous, meaning coming in at different update rates. Something that can provide performance guarantees in some sort of fault agnostic manner. So what we're used to seeing for integrity guarantees, at least in the GPS world, is this idea of a probability of misdetection, which means we assume a particular size of a bias, 5 meters, 10 meters, 20 meters, and then that creates a distribution for the fault present distribution. We wanted to kind of shy away from making any assumptions about what the fault present condition or the fault present test statistic looks like. And so how do we still provide any type of guarantees when we don't assume a probability of misdetect? And then something that obviously could scale to not just one sensor failing at a time, but maybe 2 or 3 or 4 sensors failing simultaneously, which has also been done in the literature. But we wanted a sort of an algorithm that could do all this, hopefully, in a way that is all in without changing much about the mathematics or the way that we apply it. So as it relates to number 4 here, really easily scalable would be probably the better way to put it, because a lot of algorithms are very scalable already. And then obviously we wanted to compare it, because we do have state-of-the-art methods out there. The main one that we'll be looking at is normalized solution separation, which is where our a lot of our military aircraft use for integrity monitoring. And so we wanted to compare at least how we do against normalized solution separation in both a all source and a sort of standard kind of GPS INS scenario. So these are the things we'll be looking at throughout this presentation. And these are all the things that we looked at in the paper that we're presenting off of. So when we're looking at existing methods, as I already alluded to, we want to be able to have an algorithm that is all source, that is sensor agnostic, fault agnostic, but also compares favorably to existing methods. The first thing we did is just look at what are the methods that are out there. And what we found is that right off the bat, when you're looking at the 2 different sort of categories of methods, we've got on one side what we call the snapshot fault detection methods. And this is very applicable to satellites. When you have 6 or 8 or 10 satellites visible at every sample, even without a filter being present, you can then do fault detection. You can tell which of the satellites is erroneous, if you will, because you have so many satellites at every sample. Now, the other side of that is when you don't have that redundancy guaranteed at every sample, which you can also do with satellites, but also mostly applicable to sensors like the ones we're looking at today. That's what we call the family of filter methods, using the filter statistics of either one or many filters to be able to tell whether or not one of the sensors in the system or many of the sensors are faulty. So when you look at filter methods, really the most prolific method of the filter methods is the normalized solution separation, which is here on your left. The normalized solution separation is sort of summarized here. You've got the detection of the fault itself. The test statistic is based on the difference between the solution provided by a main filter, which is informed by every single sensor in the system, and then the solution provided by a series of sub-filters, which are potentially excluding one or many sensors that the main filter is taken into account. And so when you look at the statistical differences between those n differences, you can then do a chi-square test, and there's a known distribution for what those differences should look like, and you can sort of detect when there is a fault. Now, to identify the culprit sensor, there's actually a little bit more that goes into it. If you read the patent that was sort of most prolific related to normalized solution separation, you see that even, so the detection is using solution separation, but then the ID, you either have to then do a secondary sort of exclusion where you exclude more than one sensor, or you have to go into the residual monitoring anyways to be able to do the ID of which of the sensors is the one causing the problem. This is an issue that happens with filter methods, right? Because when you have a bunch of sensors informing a single filter, just because the filter statistics are incorrect doesn't mean that the one sensor that you're looking at in terms of residuals is the culprit. It means one of the sensors in the system is a culprit. So you got to do a little bit of deeper investigation to figure out which one it is. So in solution separation, the test statistic for detection is using literally the difference between the main filter and the sub-filter in terms of solution. A lot of times we use position, right? Either the 2D or 3D position vector as the vector that we test, but you could test the entire state space if you wanted to. And this is really effective, as we saw in our research, for really faults that actually corrupt that solution, that difference, right? When you have a fault in a particular subfilter that causes the subfilter to move away from the main filter, then you know that there's, that's observable, because now that difference is actually observable in the solution space, in the state space. What it doesn't do so good at is faults that don't actually influence, things that are not biases, essentially, that don't influence or increase the separation between the main filter and the subfilters. And here again, as I alluded to, the integrity piece is usually done by defining the type of fault you're willing to accept, the size of the bias, and then defining a probability of misdetect and what that means for your system when you would sound an alarm, basically when you exceeded some sort of, when the probability of misdetect is connected to a particular sort of offset in terms of meters. Now, on our side is the proposed method. And as I've always done in my research, I try to come up with something catchy that people can remember. So the acronym for this is SARM, sensor agnostic, all source residual monitoring. It is residual monitoring. And so what you'll see is that the detection is the chi-square test that we're used to doing with residual monitoring. But I think what we have some innovation here is that also the identification and the exclusion and the integrity are all tied to this one single sort of mathematical definition. And we'll get into that in just a bit. The test statistic is really a running window, so a sum of chi-square distances over a particular user-defined window. In the examples that I'll show you, it's usually about 30 seconds. So there's a trailing window of 30 seconds where you're looking at all the residuals summed up. And what we found is that actually effective across a wider variety of faults. So normalized solution separation is very good at something that induces a bias into the system. With SARM, what we're looking at is not as good as normalized solution separation with biases, but it is much better at other things than normalized solution separation. And we'll look at the raw curves here towards the end as far as how they compare. And then we're going to get into here, which is something that we're also including here, is the idea of this integrity, not in the normal sort of capital I integrity sense, but let's call it lowercase I. We'll talk about what that means in just a second. But really, what does that mean for the user if we don't have a fault size or a fault type defined? How can we then still provide any type of guarantee? We'll get into that. So that's really what we'll go over here, is really how our SARM algorithm is capable of performing these tasks. At the core of the SARM algorithm is something that we call the T matrix, or the test results matrix, or the detector matrix, as you want to call it. And just to cage your eyes here to this figure, we got a variety of sensors. They're heterogeneous. They are asynchronous. It could be 2 satellites and MagNav and BizNav and DTED and an altimeter or something like that. Those are all producing measurements. And as we know from the standard sort of Maybeck notation, that measurement vector is called Z, and the measurement error covariance matrix associated with that measurement is R. And so on the rows here of the T matrix, you see that each row is informed by a separate sensor, sensors 1 through I, as we call it in this paper, each of them providing measurements and measurement covariances at different rates and different dimensionality, right? The Z for sensor 1 could be 1-dimensional, such as a pseudo-range, but the Z for sensor 2 could be 3x1, which would be like a 3D position measurement or a 3D velocity measurement. And the Z for sensor 3 could be a 1x1, meaning a 1-dimensional altitude or something like that. So we're not constraining anything about the dimensionality of Z or R. On the columns of the T matrix, we have subfilters. It says filter there, but they're really the subfilters of the system. Notice the one thing here that is different is that the main filter does not play a role at all, really, in this detection, exclusion, or integrity process, as we'll get into. The main filter is sort of there for the user, but it is not used in any computations in our method. Each of the subfilters is informed then by a particular set of the sensors, a subset of sensors. Now, in the simplest case, we assume that only one sensor can fail at a time simultaneously. And so what we have is a set of filters. The mathematics behind this would be n choose k. In this case, it would be I choose 1, which is also equal to I. So in this case, we have I columns, but is not limited to I, as we'll get into later. Each of these subfilters in this example then is excluding one of the sensors. At the intersection, at any cell of the T matrix, for example, in this cell here is informed by the second sensor and the third subfilter. There you have a residual that you can record at every time step, right? You have a residual between the Z produced by sensor 2 along with its R, and the Z hat produced by subfilter 3 along with its sort of covariance about Z hat, which is we call PZZ, and I'll get into the math for that later. In there, over a period of, let's say, 30 seconds, you can do a sum of chi-square test and see if it exceeds the particular threshold for the probability of false alarm that you care about. So what this ends up being, this T matrix at any given time is full of zeros and ones. Whether or not the particular sensor subfilter combination has failed the chi-square test for the residuals that are paired up between that sensor and that subfilter. As we get here into the math a little bit, so what we have here on the left is the T matrix for an example where we have I sensors and I subfilters, because we only care about one simultaneous fault, so we only need to exclude one sensor per subfilter. Note here also something that's slightly different from other methods is that we, right off the bat, the diagonal of this T matrix in this example is already set to 0. We basically set to 0 the entries in T where that sensor doesn't inform that filter. So the main thing here is that we have a residual sequence over a number of seconds. Each residual is composed again by the difference between Z and C hat. Z comes from a sensor, Z hat comes from a subfilter. And then the covariance about that residual, as we call PRR, is then R plus PZZ. Now, PZZ depends on the type of filter you have. In the Kalman filter and EKF scenario, that quantity is known to us as HPH transpose. So in this case, PRR for an EKF would be R plus HPH transpose. In an UKF, though, the PZZ, one of the innovations of the UKF is that it has a better way of producing PZZ. And so it's not constrained to just Kalman filters or extended Kalman filters. Once we have that, we define sort of a measurement time window, a time period. Like I mentioned in the examples I will show you, that window is 30 seconds. Over 30 seconds, each sensor can experience a different number of samples. If I have an update rate of 1 Hertz, then over 30 seconds, I have M equals 30 samples. If I'm at 2 Hertz, M equals 60. And so for a fixed monitoring time, the chi-square test for a particular sensor subfilter combination is going to be composed of a different number of samples, meaning a different number of degrees of freedom for the chi-square test. But what you see here is a standard sort of Mahalanobis distance, right? It's R times its covariance inverse times R transpose times sigma inverse R. That is a chi-square test statistic, and when we sum M of them over the past time period, we know how many degrees of freedom it has, and assuming that they're independent, we can form a chi-square test there. Now, again, as I alluded to, the T matrix is then full of zeros and ones, whether or not that particular combination of sensor and subfilters exceeds or does not exceed the threshold that is set by this test statistic, right? The chi-square matrix given a probability of false alarm, which we'll get into what that means for a family of tests, with the degrees of freedom that is indicated by the number of samples times the dimensionality of the Z that goes along with that row. So as you'd imagine, a satellite over 30 seconds at 1 Hertz has 30 samples, each of them one dimensional, that's 30 degrees of freedom. But a position sensor with 3D measurements at 2 Hertz, that's 60 times 3, that's 180 degrees of freedom for that same test. So that's how the T matrix handles asynchronous and sensors that are not heterogeneous. They have different update rates and they have different dimensionality of Z. It's all really set by a fixed monitoring time period and then adjusting the degrees of freedom for the chi-square test for the number of samples that were found in that fixed monitoring period. All right, so in this, as we get into here, we're gonna see how then we do the fault detection and fault exclusion. In this example that I'll run through here is just an animation, and I have actual 3D animations later, but in this example, mathematically, what we're looking at here, in this case, when we have a T matrix that is full of zeros, let's assume at this point we have a system that is navigating with the 5 sensors and it has 5 subfilters indicated by a 5x5 T matrix. The bolded zeros are always going to be 0 because that sensor has been excluded from that subfilter, so that entry is automatically 0. But what we're looking for here is patterns of zeros and ones to be able to tell whether or not there's a fault and to be able to tell who is the culprit that is causing these faults. Because one of the things that we realized quickly as we started to get into this research is that just because your residual sequence fails the chi-square test doesn't mean that that sensor that you just tested is the culprit. It just means that either the sensor is wrong or the subfilter itself has been deviated from the truth by the other sensors. And so it's really hard to tell by just looking at one combination of sensors and subfilters as to which of the sensors is the culprit. So we'll do sort of a little mental exercise and we'll do a little Q&A at the end. Otherwise, this maybe would be a little bit more interactive in person. But for here, I'll just sort of lead the discussion and you guys can sort of think with me. At this point, we have zeros, and so it's no faults detected. All is running well. And we haven't talked about integrity, but you would sort of color that green, if you will. You know, everything's good to go. At some point, one of the sensors starts experiencing a fault. What that means is that any sensor that is touched, any subfilter that is informed by that sensor is liable to potentially deviate from the truth. It's liable to be inconsistent. And so when we look at here, any single entry in this T matrix that is not a 0, it tells us that somewhere in the system, one of the sensors is potentially faulty. Now, at this point, we know there's a fault, but we can't tell the user who the culprit is just yet. The reason being is because the way that we find out who the culprit is only when there's only a single subfilter remaining fault-free is when we are able to tell that the sensors excluded from that subfilter are the ones that are faulty. In this example, one of these sensors is causing subfilter 2, subfilter 3, and subfilter 4 to have bad residual sequences against sensor 1, sensor 3, and sensor 5. But we can't tell which sensor it is that's causing the faults. We just know that the 3 subfilters are currently likely to be inconsistent, which means their error statistics are not consistent with the true errors. And we know that at least 2 of the subfilters appear to be fault-free. As you would imagine, then, as soon as one of these 2 subfilters experiences a fault, we can now tell the user which of the sensors is faulty. Now, can anybody think which one of these? How do we know which sensor is the one that's sort of faulty? As you would imagine, likely, you would probably hone in with your eyes on this sort of beautiful green column of all zeros, right? This means that this subfilter, for some reason, is fault-free. Now, the cool thing about this is that based on the way we've designed the subfilters, at least in this scenario, this subfilter excludes only one sensor. And so it is the sensor that was excluded from this subfilter, the one that we are going to call faulty. The reason being is that because everybody else is experiencing some sort of fault, and the only way we don't have a fault is when we exclude this sensor. Now, you could imagine how we extend this, right? So if I want to assume that 2 sensors can fail at a time, I'm going to keep this T matrix for a 1 sensor configuration, and then I'm going to build a second T matrix with an n choose 2 type of number of columns. In the case of 5 sensors, that would be an additional 10 columns or an additional 10 subfilters. So the con to this is, right, the computational efficiency of running hundreds of subfilters. But if you can do it, it works pretty well. And I have an example at the end where I show you a double simultaneous fault. In that case, let's suppose this was a sort of n choose 2, then still the same rule applies, which means the sensors that were excluded from this column are the ones that are not faulty, if that makes sense. All right, so now we've talked about fault detection, fault exclusion, and essentially, fault detection, identification. Of course, exclusion at this point would mean that we would throw away all these subfilters that are faulty. We would then take this subfilter, which is only informed by n-1 or i-1 sensors, and we would use this as the basis to respawn an entirely new T matrix that is now informed by 4 sensors, because we just threw away one of them, and then 4 subfilters. We would sort of reshuffle this, knowing that this one is consistent at the beginning. We'll see how that works in the animation in just a bit. All right, so now what about integrity? Because at the beginning I talked about we want it to be fault agnostic, sensor agnostic, heterogeneous sensors, asynchronous sensors, and that all works well with the T matrix in terms of fault detection and exclusion. But what about providing integrity, some sort of integrity guarantee to the user in a way that doesn't constrain the fault type? I don't want to say a 10-meter bias is my basis for integrity. I just want to say it could be a bias. It could be the R matrix that is wrong. It could be the H function, H equals Z equals H of X. It could be any of those things that are wrong. I don't know, and I don't want to assume. So how can I still provide any type of guarantee? So as John Raquette, my advisor, often told me, there's a couple of different integrities out there, right? There's the very rigorous capital I integrity, which is very rigorously mathematically defined. And there's this other integrity that is sort of the best we can do if we want to be fault agnostic, which I would call lowercase I, and it's simply just a guarantee of system performance under a specific set of assumptions. So as long as the user understands the assumptions, then they're able to to act on the information that is provided by this type of integrity. And so we'll talk about how we develop that for this algorithm. So I have about 4 of these sort of still shots here, and then we'll have some videos to show. What we have here is sort of our depiction of integrity for the SARM algorithm. The name that we gave it, again, I love acronyms, and so the name that we gave it is GPZ, because we didn't want it to be confused with HPL or anything that is super rigorous, right? It's really a very simple, yet in our mind, elegant way of defining integrity, at least in the position space, but it can be really expanded to any portion of the state space. The GPZ is the guaranteed positions zone. It just really means to the user, we recognize that a filter's error statistics are only as good as the assumptions going into the filter. And so if we have a fault, whether it's detected or undetected, we know that some of those filters are going to be inconsistent, as we call that, meaning that we cannot trust the error bounds that are drawn about their P matrices, their covariance matrices. And so what we have here, we know that in the T matrix, one of the subfilters is sort of guaranteed to be error-free because we've designed it in a way, right? The assumption that the user has to understand is how many sensors are allowed to fail simultaneously. So in the case of one simultaneous sensor fault, we know that if I exclude one sensor from each subfilter, then one of the subfilters is always guaranteed to be fault-free because only one sensor can fail at a time. And if only one sensor fails at a time, then one of my subfilters excludes that sensor, which means its error statistics are correct or consistent. So in this case, again, we're running through the T matrix again. We have no fault. You'll see here which sensor is being affected by the fault, how much of a bias. In this case, we're using a bias just to sort of demonstrate. We could also use a scaling of the R matrix as another type of fault, and sort of the time along the simulation. These are the figures from the paper. We have a system that is all source. We have 4 sort of all source sensors. One that is a velocity sensor. We have 2 velocity sensors and 2 position sensors, no satellites in this case. And by the time the simulation crosses this red triangle, that's when the bias starts to grow. So before we cross the red triangle, we have no bias, and SARM tells us there is no fault. So all good to go there. The GPZ is then composed of the union of all these subfilter error bounds. So we say 95% GPZ, then I draw 95% error bounds around each subfilter, and I union them. And I know that somewhere in that union, one of them is consistent, which means one of them is guaranteed to contain the truth. At least, 95% of the time, if I drew a 95% error bound for everybody. Notice I haven't said anything about the main filter. The main filter does not inform the GPZ in any way. It's really all about the subfilters, because all I can assume is that one of the subfilters is guaranteed to be error-free. Regardless of whether I've detected the fault or not, one of those subfilters is not taking measurements from a faulty sensor, if only one sensor can fail at a time. So let's progress along the simulation. And now 49 seconds into the simulation, I have a bias of 1 meter per second being induced into the VEL1 or a velocity sensor. This velocity sensor is analogous to, for example, a visual aided navigation sensor that does sort of frame to frame tracking, providing some sort of velocity information. In this case, notice that even though there's a 1 meter per second bias into the VEL1 sensor, the T matrix has not reacted to it, right? The bias is too small for any of the chi-square tests to fail. So we have not detected the fault. So no fault detected, even though there is a fault. So what can we do with that? Well, the GPC is still valid, because I know that even though I haven't detected any faults, if I knew which of the sensors was faulty, in this case, I know the VEL1 sensor, the VEL1 sensor's error bound contains the truth. And if I union it with all the other sensors, because I really don't know who is faulty right now, then I know that in that union, one of them is bound to contain the truth. So I can at least provide this guarantee to the user, that your estimated position is here based on your main filter, but that you could be as far away as this based on a non-detected fault. Now let's keep growing the bias a little bit more. So another 30 seconds later, the bias is tripled. There's now 3 meters per second into the same sensor. Now notice the T matrix is starting to react. Now in this case, again, we have the case where I have a fault detection, but I do not have identification yet, because I still have 2 subfilters that remain fault-free. So I do not know which of the sensors is actually causing the fault. Still then, I can still provide a GPZ to the user, because now we know that somewhere in this union, once again, one of these error bounds contains the truth. I don't know which one, but I union all of them, and one of them contains the truth. Notice that the main filter is completely inconsistent. It does not contain the truth within its error bound, but the GPZ still contains the truth. Now, here is where you could set some sort of alarm, right? You could sort of connect this to an alarm limit where you say, hey, when the GPZ major axis grows beyond X meters, give me an alert telling me that I shouldn't be using this for, let's say, a precision approach or dropping a weapon. So that's a form of integrity. It's probably a bigger than what you would have when you assume a particular misdetect rate, but it's something that allows us to be fault agnostic. Now, finally, we progress, I think, another 0.1 seconds or 1 second. The bias grows to 3.1, and now I know, because now the T matrix is all, there's only a single column of zeros remaining, which means that whatever sensor was excluded from this subfilter in position number 1 is the sensor that is faulty, because when included in other filters, it causes them to be faulty. When excluded from my subfilter, my filter is fine. And again, as we see here visually, this is the no vel1 subfilter, which means the subfilter that is producing this column of information. And it is his error bound that is the one that is actually consistent. Again, up until this point, we don't know which one it is, but the GPC appears to be valid. After this frame, we would then throw away all the other subfilters and restart with a clean subfilter based on this filter. We would make this the new main filter. And then we would then recreate a series of 4 subfilters, now excluding each one of the, 3 subfilters, now excluding each one of the 3 remaining sensors. Hopefully that makes sense. And now we'll have a video to sort of show that, and then we'll go back with Q&A to sort of close the loop on that. So that's how we provide the fault agnostic performance guarantee, the GPZ. So now here's 2 examples. I believe I have 3 examples to sort of demonstrate the system performing across a variety of situations. So this is an all source system. What I mean by that is I have 4 satellites, 4 pseudo-range satellites, with clock error and all the sort of high fidelity simulation there in 3D space. I have 2 3D position sensors, 2 3D velocity sensors, and I'm doing error states, which means I'm doing INS resetting, and I'm running with an HG9900 IMU. What we'll see here in the video at the bottom, let me start the video. We see here is I assume 1 sensor can fail at a time, so I have only 1 layer of T matrix subfilters. I have here the vel1 sensor is going to be faulty with a bias. The bias will start to grow here, and we'll see how it sort of reacts. And we can see it both on the horizontal plane and the vertical plane. See that the sensors are asynchronous, as shown by the little blinking lights there. Again, 9900 IMU with a Pinson 15 error state model. And as we see here, actually just sort of played, the system was able to detect successfully that the vel1 sensor was faulty by taking it out of the set of filters. And I'll just go ahead and play that again so we can see. What we have growing underneath, right, is the GPZ, which means is the union of the error bounds of all the subfilters. And that is where you're guaranteed to be 95% of the time if you're using 95% for your error bound computations. After the fault grows, again, the GPC is always valid. We have sensors that are different dimensionality of Z, different update rates. Using error states in 3D space, there you have detect but no ID, and then when it turned orange, you have the ID and then the throwing away of that sensor and then reshuffling of the new T matrix. So this is a standard sort of, kind of what's already out there. This is a bias on a velocity sensor. Nothing too cosmic here, but again, SARM is able to perform. Now, without changing any of the math or re-specifying anything about the mathematics going on, we now move to a different type of fault. In this case, we have the same all source system, but now the fault is not a bias, but a scaling of the velocity of the position sensors R matrix. So the R matrix that is stated in the error model, so what the filter thinks R is, it's going to differ from the actual R is in terms of what the noise that is induced into the system for measurement error. And so we'll see how that reaction happens here. What we'll see here, and as I'll show you in the raw curves, is that the subfilters won't really be too far separated from the main filter. And so as a preview, you could see that solution separation actually wouldn't be as good as detecting this, because there is not much difference between the 2 solutions, between main filter and subfilter. However, in the T matrix, which does not look for differences, it looks for statistics, including covariance, there we see that it quickly and effectively detected that position 1 fault with no re-engineering of the T matrix or the math behind it. It's the same chi-square test, the same integrity applies, even though the fault is now different and it's on a different sensor. So we went from a bias on a velocity sensor to a scaling error in a position sensor, the same math, the same T matrix, the same integrity. Finally, we have a sort of the next level, right? So we assume 2 sensors can fail at a time. And so now I have to have 2 T matrices, one for detecting one failure, and the second T matrix for detecting a double simultaneous failure. In this simulation, we'll see that satellites 3 and 4, I believe, yes, 3 and 4, are going to fail at the same time. So the same bias will be applied to both of them at the same time. And we'll see is that the GPZ still holds. In this case, the GPZ for level 1 will be incorrect. That would be indicated by a T matrix full of 1s. But the GPZ for layer 2 or the T matrix excluding 2 will actually have a row of 0s, which means that one of the subfilters, particularly the one that excludes both SAT3 and SAT4, will still be correct, or at least consistent. We see here detect, but no ID. And it takes a while for ID because the biases are growing sort of at a slow rate. And then we have ID and a simultaneous detection of 2 satellites failing at the same time. And here, another thing to note is that out of the 4 satellites, 2 failed, and we were able to do that detection and exclusion using the all source sensors, using information from the position and velocity sensors, as well as the other 2 satellites. Again, without changing the math, without changing the chi-square test, or without changing our definition of what integrity means for the user. So that's sort of what's going on in terms of performance. Now, just as a preview, what's going on there with the T matrix and the way that these sort of alluding to what the raw curves are going to look like. Here's an example T matrix for a system with 4 sensors, so 4 by 4. I'm not including the diagonal because we know that those are supposed to be zeros. And you can see here that when this is based on 10,000 runs of Monte Carlo, with 10,000 of them running with no bias in the system, and 10,000 running with a 1 meter bias on Bell 1. And what this shows is sort of the distribution of the test statistic given the 2 conditions, the H0 and the H1 condition. As you can see here is the separation between these is what sort of allows us to do either good detection or bad detection. The shape of the raw curve really comes from the best curve that we can draw out of these different scenarios here. For that same scenario, which is a bias, when we look at solution separation, we notice that it is it's a lot better for solution separation to detect that bias, because for this subfilter, particularly the one that excludes the velocity 1 sensor, the solution, the difference between the H0 and H1 test statistics is a lot more pronounced. And so you can see why solution separation is a lot better at detecting this bias, as I'll show you in the raw curve. Now, when we switch the fault over to a scaling, so in this case, we're not another 10,000 with no fault, and another 10,000 with the fault being a 2 times scaling on the R matrix of L1, we see here now that the T matrix actually contains very nice separation between H0 and H1, which means we're going to have a nice detector. We're going to have a nice raw curve coming out of that. When we look at the solution separation for that covariance case, we see that there's not much separation because, again, a change in error covariance matrices does not induce a difference in position solutions. And so naturally, solution separation won't be able to pick that out as well. And this would result in a much worse raw curve than we saw before. So what does the result in? Here's the 2 raw curves. Each of these is informed by essentially 20,000 runs, right? 10,000 H0, 10,000 H1 here, 10,000 H0, 10,000 H1 here. What we see here is when the fault is a bias, when the fault actually moves the subfilter solution, then solution separation is actually better than SARM by about 17% in terms of probability of detect at the sort of optimal detection point, or when lambda equals 1, right? When the slope of the curve equals 1, that's the Niemann-Pearson point. And so we chose to do our comparison at that point. And there, at that point, solution separation has a 17% better probability of detect than SARM. But then when we switch the fault to a different type of fault, which is mostly involving extra noise, but zero mean noise, then SARM actually outperforms solution separation by 81%, again, at the Niemann-Pearson optimal detection point. So what we have here is really even though SARM, we recognize that solution separation is still sort of one of the most applicable methods here to use when you have a nicely stated probability to misdetect, a nicely stated sort of fault, which is a bias. When we sort of want to go agnostic of that, we sacrifice a little bit in detection of your conventional faults or your biases, but we gain a little bit more in the other realms, which is sort of this other idea where my sensor could be off in a number of different ways because it's an alternative navigation sensor that we haven't studied for 30 years like we have for other sensors. In terms of probability of false alarm, right? We also want to make sure that the probability of false alarm that is actually experienced by the system is consistent with what the user selected. What we have here, the T matrix, is actually a eye by eye sort of number of tests minus the diagonal. And so from a Bonferroni perspective, in terms of a family-wise probability of false alarm, what we do is we program in the Bonferroni correction into each of the cells of the T matrix in order to guarantee that the probability of false alarm experienced by the entire system is less than or equal to the desire. So we're never getting more false alarms than the user thinks they're getting. So that's and so essentially to cover that case, the fact that the T matrix is full of a number of tests and not just one test, each of those tests has an alpha value to it. We have to account for that using the Bonferroni correction. And then when we look at the GPZ in these scenarios, again, this is all based on the Monte Carlo. When we have fault-free, the main filter covariance, of course, is consistent. It matches the 95% expected value. The SARM GPZ, again, because we're doing a union, we actually don't mind if the GPZ is larger than 95%. We just want to make sure it's not less than 95%. Again, just like the probability of false alarm, we don't mind if it's less. We just don't want it to be more than what the user expects. When we induce a bias, the main filter covariance, of course, is inconsistent because it is informed by a bias sensor. The SARM GPZ, of course, contains still at least 95%. And then when the fault is a scale, the main filter is almost there because, again, we're not really messing with we're not biasing the filter. However, it falls less than 95%. Meanwhile, the SARM GPZ still covers the at least 95% case, which is what we were looking for in terms of guarantees to the user. And that's sort of the bumper sticker there. Okay, so I think that brings us to conclusions. So this is the paper, right, that was published in ION's latest publication. We wanted an algorithm, and hopefully I've shown you at least convincingly enough through the presentation, and of course, welcome to read the paper. Something that detects and excludes faults in a sensor and fault agnostic manner. So we're not assuming what kind of fault we have. We're not assuming what kind of sensors we have. We can let those vary as they need to. Works with asynchronous sensor, meaning sensors that are coming at different update rates, sensors that have different dimensionality of Z, and sensors that provide different degrees of freedom, basically, for the chi-square test. It provides this idea of the GPZ, the fault agnostic lowercase I integrity, which is the guaranteed performance, guaranteed position zone, actually. So that's a typo there. And then can detect and exclude the faults, regardless, so that the GPZ is sort of valid regardless of the fault exclusion or detection status. And it compares well enough to solution separation, right? When there's a bias, solution separation is still sort of the state of the art there. But when we want to sort of relax the assumptions there and say, hey, this could be any type of fault, we lose a little bit in terms of bias detection, but we gain a lot in terms of detecting other kinds of faults. For more information, so this is how you can find the article, and if you want to read it and cite it, that appears there in the article. I was the sort of primary author as is part of my PhD dissertation. Dr. John McCoy was my advisor. Dr. Christine Schubert-Caban, she's a professor at the Department of Statistics at the Air Force Institute of Technology. She was a co-author and on my committee. And then Major Jonathan Gibson, he's a PhD student who also helped me work out a lot of these sort of test cases. So between the four of us, put together the paper, and welcome to reach out to anybody. But primarily, if you have any questions, you can sort of reach out to this address for further discussion. So that's the sort of end of the presentation. I'm going to go ahead and open up the Q&A and see what we got going on here. Okay, so I have one question. It says two questions. So I'm going to read the first one. Once a fault is identified, the sensor is excluded. Does this assume that a faulty sensor does not have a chance to recover? That's a great question. So I'm going to answer that one real quick. So yeah, so as a sort of as a plug to another paper that is also is actually an ION conference paper. It's called autonomous resilient management of all source sensors for navigation. There we cover this scenario, right? Because once you lose the sensor, you also want to give it a chance to recover. And so in RMS, which is the more overarching algorithm, we cover the idea that when you throw away a sensor because you've identified that it's faulty, you actually want to then have a mechanism that allows it to come back in. Meanwhile, the entire time your GPZ is valid and you're not sort of messing with the user's guarantee. So we have that. I would sort of point you to a paper called Autonomous and Resilient Management of All Source Sensors for Navigation Assurance. That is actually the title of my dissertation. It is a conference paper from PNT 2019 in Hawaii. You can look that up, and that's where we sort of cover the idea that the sensor needs to come back. Because again, when we have a navigation sensor, whether the fault is temporary or it was sort of a spurious fault, we don't want to just throw away that sensor forever. So that's a great point, and we cover that in a separate paper. This paper was mostly focused on the FDE function. Hopefully that answers your question. We have another one from John Quarantaro. It is not uncommon in real world situations to have an error model which doesn't perfectly match the true errors. Sure, if SARM triggers more reliably on R mismatch, could that lead to a high false alarm rate due to imperfect error models rather than actual faults? Any thoughts of how to handle this? Yes, that's a great, another great question, something we sort of looked at a lot during the algorithm. I would, again, at the risk of sounding like a used car salesman, I would point you to that paper again, the RMAS paper, ARMAS, where we cover the situation where, yeah, you're right. If you have an incorrectly stated R matrix, you're probably going to get a fault from SARM, the FDE algorithm. But what will likely happen is we've provided a mechanism in RMAS for the user to say, hey, if this happens, here's some options to try. One of them meaning, one of those options could be increase R or decrease R, or here's 5 different types of R to try. And that's where we get into sort of the MMAE aspects of this, all aimed at bringing the sensor back. Another thing that we have that's not in this paper is sort of a second layer called the validation step, which we use to bring in untrusted sensors that are not online when you first start, or when a sensor has failed and it claims to have fixed itself, you sort of have a separate validation scheme before you let it back into your pool of trusted sensors. So you're right. When you have when SARM is triggering off of R, which I've just sort of demonstrated as one of its sort of benefits, you have the possibility of getting false alarms because you, as we often do as alt-nav researchers, we often sort of guess at R a little bit until it works. And so in that case, you would either offline figure out a good R until you're sort of comfortable with what SARM is doing, or provide through RMIS, the other paper, the mechanism to sort of update R if you sort of end up faulting that sensor as a way to bring it back. You would sort of run into a change R over to validate loop until validate passes, and then you get back into the game. You're sort of, the coach puts you back into the SARM pool of sensors. Hopefully that answered that question. Another question from Danielle. Could you give an example where the fault causes what you describe as Zeromean errors, scaling your example? If I understand the question correctly, scaling of the R. Yeah, so this would be, for example, kind of like what John just alluded to. If I, as a researcher, incorrectly plug in an R, I'm saying, hey, I have a VisNav sensor and I think R is, 1 pixel square or something like that. Of course, there's a lot of math, there's a lot of research going on into what R even means specifically for visual aided navigation. But let's say I have even a position sensor that claims to be, within 10 meters square in terms of R, and I type in R equals 10 meters square to the filter, but the real R is actually more like 20 meters square. SARM would sort of pick that up, and you would say, hey, this sensor is, we're used to saying the sensor is faulty, meaning there's a bias, it's going to throw away my solution. In our case, we're saying it's faulty, means its error model does not match its observed model. The stated model doesn't match the observed model. So we actually would want to kick that sensor offline. And this is where RMS, the other paper, kicks in, because we want to fix it. We don't want to just throw it away because it has a bad R. We want to go fix R and then bring it back through validation and then back into SARM. So an example, I think a real world example would be where, as a researcher, I'm working on a new sensor and I just sort of take a guess at R, and that R is actually incorrect. It doesn't match what is actually observed during real navigation. And so SARM would help you pick that up and then clue you in that you need to fix it. So some would look at that as a sort of a false alarm. we, in one context, would look at it as a good thing because we want SARM to tell us that R is wrong. And then we want to then kick that into a sort of a separate loop that fixes R for us because we've detected a bad covariance matrix. Next one, thanks a lot for your answer. I'll check out the paper. Okay, another question. Why do you take the residual instead of the innovation? Many papers state that innovation is more sensitive to the fault and make it easier to detect. Yeah, this is actually getting into the weeds, and we actually read a lot into, what's the best, what is the best sort of statistic to look at. So once you're into filtered methods, we sort of have a choice. And I think maybe what you're aiming at is, I've seen two different papers, at least that are prominent out there. One of them takes the pre-update residual. So the Z minus Z hat, which is based on X minus, if you're familiar with that notation. And one of them is based on sort of Z minus Z hat based on X plus, so after the update. What we found out is that based on the literature and sort of, here at the Air Force Institute of Technology, we're sort of have learned under Dr. Maybeck for quite a while. And so we have a lot of the mathematics and the approaches that he took in his research. And so for us, we were a lot more comfortable, really, just honestly, with the statistics of the pre-update residual. We actually could tell using our simulations and our raw curves that everything was sort of matching up as expected. So we could better theoretically predict the pre-update residual statistics. It is well proven that the pre-update residual sequence is a white sequence. So we want to, that chi-square test is fully dependent on the sequence being independent, meaning that the residual one at time 1 and residual at time 2 are completely independent. And we just sort of proved it to ourselves first that the pre-update residual is an independent white sequence. Not to say that the post-update residual is the same, but honestly, it was just something that we felt more comfortable with. And we did a little bit of investigation with post-update residual, and we sort of started to get some interesting, not as good results. And so we sort of reverted back to what we felt comfortable with. I think there's future in research. Maybe this could get a little better if we really nail down those post-update residuals, or the innovations, as you call them. And maybe that'd be a little bit more sensitive. The other thing that I would offer is that once you've applied the update, you have kind of a one sample sort of difference by the time you sort of realize something's wrong. Could be minor, but that's a potential consideration as well. Okay, final question. How does your method of FD impact the computation of protection levels? Yeah, this is a great question. Admittedly, I gotta really admit, I did not go really deeply in my research into sort of meld, at least not at this point, melding the two, right? Melding FDE, the GPZ that we're proposing, and your standard rigorous protection levels. Now, what I would say, something I alluded to earlier, is that you could, and this was based actually on a comment from one of our reviewers for the journal, you could actually then sort of wrap around this an alert level, meaning if your GPZ exceeds the GPZ is a weird sort of and a morphic kind of figure, right? So we call it the amoeba in our team, right? It doesn't have to be an ellipse. It takes on many shapes. So you'd come up with some sort of measure on that ellipse, whether it's the longest sort of possible distance between the main filter and the edge of that GPZ. If that exceeds some sort of level, you would have an alert. As far as protection level, my understanding is that once you want to have a protection level, you have to then assume sort of a probability of misdetect. And that's where sort of you derive the protection level from. So I think to melt the two, we would have to lose a little bit of the agnosticism that we've tried to sort of motivate this paper with. So my answer would be twofold. Number one, I am not an expert enough in protection levels to sort of answer your question fully, but I will say is that we do have a way to have an alert level or in GPZ by alerting the user if the GPZ grows beyond a certain amount that they're not comfortable with. Hopefully that answers your question enough. I think in sort of as we continue this research, a natural progression is to meld the two and so have a system that actually is informed by both. You can have a system in ARM as we propose, you have many monitoring tests. And in this case, we could have a solution separation with an assumed bias level for protection level doing its own test. And we have SARM also doing another test. And then you can sort of programmatically decide between the two as to what the user is going to see and how as you go along. In general, I think what our research team has been aiming at is this idea of sensor management in this new era of all source asynchronous sort of sensor agnostic way. And between this paper, SARM, and the other paper that's also in ION, which is a conference paper called ARMIS, Autonomous and Resilient Management of All Source Sensors. We've tried to sort of put that story together between the two, and hopefully, if you can find the two, that'll generate a lot of good discussion that we can have afterwards. Okay, that is the last question, and I think we are closing in on time. Thank you for your attention. Thank you for your great questions, and of course, feel free to reach out to my email address. Hopefully, you can download a copy of the paper, and then hopefully this recorded webinar will be posted somewhere that we can download it as members. Thank you again for the opportunity to the ION staff, and I'm hoping that this was fruitful for a lot of you. It was certainly a good opportunity for me to be able to talk about our research now that it's all published and complete. Thank you.